All right, here we go. Number 8. So this time it was interesting. I was doing a search for just physics chapter 2 or something. And it turns out, man, it seems like there's an explosion. There's just tons and tons of teachers doing it. And so now I actually almost have to filter by the language, but YouTube doesn't let me filter by the language because some of them I don't understand what language they're speaking, which is exciting, right? I mean, it shows how global this approach that everyone is taking is. So I went back to my typical search of physics homework solution. Actually, I used HW instead of homework. Anyways, came up with this. Here we go.
Number 33. Let me see if I can fix that real fast. Hopefully that'll update soon.
Oh, cool. So his data is all over the place, and he's trying to make sure that it gets updated in every place the students can see it.
If anything goes awry, anything's not working right, let me know. See, do I have my little picture of myself? There I am. Put myself over here. There's a term, contact forces, that we haven't really talked about. Contact forces are a lot like tensions, except they're pushes instead of pulls. So this person.
So let's talk about being able to see him. I think that it's a real estate question, right? Like how much can you handle covering some things up? And so you keep seeing him fiddle with where this window is going to go. I know that there's some software, Snagit, for example, it's like all or none. So you have to flip to be able to see your face, and then you can flip back to see this. And then, of course, there's whatever software you want, like what I'm using, OBS, to just sort of move your own window around. I guess I'm sitting about here-ish. So I think that there's incredible value to being able to see someone's face and be able to understand what they're saying. And so I think that there's no question that it's a useful thing to consider doing. But I'm just really curious, maybe put in the comments your thoughts about the value compared to being able to see, what's being displayed.
The person in the picture here is pushing against a box that's on a table, and that box is pushing against another box that's also on the table, and the two boxes are sliding together. So the contact force would be the force right where the two boxes are touching one another. And I could be tricky and say, which contact force is greater? The 2 kilogram forces, 2 kilogram box's force that it's applying to the 5 kilogram box, or the 5 kilogram box's force that's pushing against the 2 kilogram.
So I love this, right away going at one of the pieces that's absolutely going to show up in this problem, the sort of the Newton's third law thing that's going to happen there in the middle. I think that, my own experience when I was learning this is, well, there's 21 newtons. It just gets pushed on through because this is a solid object. Whatever I'm doing here just gets communicated there. So I was convinced as a student that it was 21 newtons. The 2 kilogram onto the 5 kilogram was 21 newtons, and that nothing is pushing back. What the heck are you talking about? It's 21 newtons this way and 0 newtons that way. And so that was me coming in, my very first sort of way of thinking about these sorts of problems. And I'm sure there's lots of students who think that way. And so I'm really curious to see how he reinforces the ideas of Newton's third law and things like that. And you can tell this is called a warm-up. So I'm guessing this should be pretty straightforward for his students. Just warm-up makes me think that it's almost like review, although warm-up could also be, let's do a problem where we're going to hit a snag, where we're going to hit a point where it's like, what? So for example, if my teacher had done this back when I was convinced, well, it's 21 newtons, gets communicated through here, through this solid, does it say what it's made of? Let's assume it's made out of metal, right? Which we'd think of as not being squishy at all. 21 newtons here, 21 newtons there, and nothing coming back. If he were to set up this problem and discuss and say, what? Like this moment of, well, I'm convinced of Newton's third law, but that doesn't help me understand this at all because it doesn't match my intuition. That, I think, could be a super awesome warm-up, too, as long as you hit it in class and say, okay, well, man, that was difficult. That caused some of you to raise your eyebrows. Let's talk about that.
Box. I guess that was tricky, but the answer is they're the same. They're equal and opposite. They're the action and reaction. So as the person pushes on the 2 kilogram box, the 2 kilogram box pushes on the 5, and there have to be reactions to those two pushes. So the 2 kilogram pushes on the person, it pushes against the 5, and the 5 pushes against the 2.
So, question for you guys. So he uses the word pushes, and I think of that as a little bit anthropomorphic, right? Like we're treating that box as though it's a real thing. It's making a conscious choice to push. I'm trying to think, I'm trying to check myself here. So pushes, I think, is a totally legit word for the word force. And if he had said the force from dot 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 and the force on this, I think I wouldn't have gone to this idea that it's like consciously doing it. But for some reason, the word pushes makes me think a person is doing it. And so I'm really intrigued by this because I know from my own learning that anthropomorphizing things can really help me. It's like, oh, okay, that electron hates that electron. Oh, so they like to be apart, right? So these ideas I think can be really, really useful.
So there are a couple of actions and reactions. The first question is, what is the contact force? How hard is the 2 kilogram box pushing against the 5? And vice versa, the 5 pushing against the 2. And then what?
So I got to be honest here. I looked up and I was like, wait a minute, we need to know a little bit more. And I realized that I had not read this tiny little phrase here, right? So this no friction phrase is going to enable this problem to be doable. Problem, number 1 there is going to have an answer. I think that, well, it'll always have an answer, but I think that if it had said this person is pushing really, really hard and nothing is happening, well, then I think the contact force question is trickier, right? Because, well, a 5 kilogram box is not moving, the 2 kilogram box is not moving. So there's no acceleration. Does that mean there's no force? Right, so I mean, and yet you can sort of squish these things. So you can imagine if you push really hard here, let's imagine super, super sticky friction. Push really hard here, and this could squish in here, could squish in here, but the friction is holding. Well, could there be some deformation going on here? And it's really the friction over here is doing more of the job. In fact, imagine this. This is no friction, and there's just friction just right here. There's like super glue right there. I know some of you don't like super glue being friction. So okay, some super frictiony Velcro something or other here. There would be some deformation here, so there would be a contact force, even though there'd be no acceleration, because it's not moving. So I think that it's a warm-up, right? So they're going with no friction. So I think this one is not going to have those issues, but I'm just constantly thinking about ways to help students in all the situations they're going to deal with. Let's keep going.
What are all the individual forces and net forces acting on each box?
Cool, I like number 2.
I think a good chance to think about different systems. And
sorry, I just realized that I cut us off. I didn't, whatever. What do you not see here? So this word is this. This is between the boxes. Oh, actually it says this causes the 2 boxes to accelerate. This is between the boxes. This is what is the contact force, and this is what are all the individual forces and net forces that are acting on each box. And you're not missing anything over here. Sorry about that.
Instead of it being with tensions, which is what we've been doing, we've been having blocks that are connected by ropes and they're pulling on one another. Now we've got a couple of boxes that are pushing on one another.
Ooh, I like that distinction. That was really cool.
So see if I can do it in my head, and let's see if anybody else can do it in your head, and then I'll actually draw some stuff. So the first question is, what's the contact force with which the 2 boxes are pushing?
This is really cool. He's saying, let me see if I can do this in my head before really drawing some stuff out. Now, of course, some people are like, oh no, you gotta draw right away, holy cow. But I think that he's encouraging his students to check their intuition, just like he's trying to check his own intuition right now. So he's thinking, okay, let's see, 21 newtons coming in, 2 grams, 2 kilograms, 5 kilograms. He's trying to think about, can he almost show off and say, ooh, wow, I bet it's gonna be this, right? Before actually setting it down and explaining it. And I think that, with students, checking their intuition, checking to see if they might have any experience that might help them understand the answer here is really interesting. It's very cool.
Pushing against one another. Does anybody know what that is?
Well, there must be an audience for this.
Give you a little longer to think.
And we can't see
I'm
even,
gonna do a few steps.
I'm telling you, I can see the whole thing. We don't see his chat. I think that's actually really cool, right? So from the perspective
And
of sort
while
of
you're
protecting your
thinking, I'm
students,
going to switch to this.
we can't see the chat in this recorded video.
You know, yeah, I'm not going to have my picture here because, well, I don't even want to try to explain why, but it's just easier to not. So before I launch into it, does anybody have an answer? I'll draw pictures of some of these forces. So this is the contact force of the 5 kilogram box pushing against the 2 kilogram box. And this would be the equal and opposite force of the 2 kilogram box pushing against the 5 kilogram box.
These problems are so tricky. I mean, again, that initial way I was thinking about it, I would already be like, what? But I think he's doing such a great job. He said, well, they're touching, there's a contact force, and it's equal and opposites. Let's trust that. Let's see where we can get here. Because right away you're like, what? 21 newtons being pushed, man, that sucker's going to move. And what do you mean there's somebody pushing it back, especially this force here to the right?
Draw some other forces just for good measure. And if anybody figures out what that is before I get to it, just blurt it out. So each of these has weight, and I'm not going to write out the formula for weight. I'm not making my arrows necessarily the right length proportional to other arrows.
Ooh, I like that.
So
I like him
weight
saying
is mass
that.
times gravity. 2 times 9.8 is 19.6. So that's the weight of the 2 kilogram block, but there's also the normal force that's counteracting that and equal to it. So that's also 19.
So number 2 in the problem asks for all of the forces. So it's important that he gets all this down. But it's interesting that for number 1, you really don't need any of this. I think students are pretty used to the fact that the vertical is sort of canceled out. But I think that because there's trickiness in this problem, it's important to say, look, we've been doing this kind of thing all the time. The box is acting on the table and the table is acting on the box. That idea, that normal force idea, is exactly the same as the contact force. And so it's such a great way to tie in the weirdness of this problem with stuff they already know.
0.6, and I should have down here said this is the weight. And then for the 5 kilogram block, there's also, yeah, I'll be.
Sorry, so now there's some distraction going on. I just wanted to pause and think about how you deal with the fact that there can be some distractions. I think students like, sort of at my school, what we're finding is the students really like finding out that their faculty are humans, right? And so we're hearing, and I'm sure you are too, tons and tons of stories of people loving when the pets are in the background, that kind of stuff. And I think that if you get interrupted, let's see how he deals with it. So I just paused it right when it happened. But my guess is he's going to say, oh, sorry about that, guys, let's get going. Or he might have to pause his video, right? So I think that there's lots of ways to interact with this. Let's see how he does it.
I'll be out with you in a little while. I'm in the middle of a class.
Okay.
Not bad.
So with this, oops, I almost wrote normal force again. So here, this is the weight. And weight is mass times G. 5 times 9.8 is 49. So this is also 49. I think I've got all the forces. Has anybody figured out what the...
It's really, really interesting to think about the torque on this table, right? So this table has one force here, just as where he's drawn it, another one here, and they are not the same. So this table wants to rotate. What's keeping it from rotating, right? And so it's really interesting just how far down the rabbit hole you can go when you start doing these sorts of things.
What the contact force is yet? No? Hopefully somebody really has, but you're just being shy and modest.
Love that. Love that.
I'm trying to erase those. So, to figure out the contact force, this is just like figuring out the tension in one of the other kinds of problems that we've done. I'm going to color this box, make this a green box, and I'll use green for stuff that I do.
Oh, I like that color
I'm
coordination.
going to work on this box.
I mean, it's interesting that he drew out a lot of the forces in red already, but
This a little bigger.
but this idea of color coordinating
This is
your
gonna be a
equations
blue
is very
box.
useful.
I'll use blue for those kinds of calculations. And then for the whole thing, I'm just going to use black. So just like with the tension problems, first thing you do is
Yeah.
start working on the entire system
Yeah.
and figure out an acceleration, and then you can go from there. So over on the right, I'm going to do the same old things I do with every
So
of
3
these kinds
meters
of
per second
problems. Let's
squared,
see that.
or
So
as
the
I
net
like to say,
force of the
3
entire
meters per
system,
second.
I'll call it
Per
net
second.
force 7 because the whole thing has a mass of 7
Oh,
equals
we're not going to see all of his
mass
calculations. Sorry about that.
times the acceleration.
It's just parentheses A.
And then the other way to do the net force is to add up all the individual forces on this, and
Oh, I like that.
is a very simple answer.
I like that.
Does anybody know? Can anybody blurt out the net
21.
force on
21.
the system if I add up all the individual forces?
Everything else cancels. It's 21.
Everything cancels except for one. All the normal 21. And I'm
Ooh.
going to write negative
Awesome.
21 because it's leftward, and so when I do the math, I want to do it this way.
Oh, that's really cool. So indicating how he's going to talk about left versus right. So he's saying, I'm going to use that negative sign to do this, which, is arbitrary. But I think as long as he's consistent, he's really not going to get himself screwed up as he does the rest of this.
So I'm not going to write out this equation. I'm just going to do it. So negative 21 is the net force, and that equals 7 times A. So these are both ways to express the net force. If 7 times A is negative 21, then A equals negative 3 meters per second squared.
Yeah. Awesome.
So that really wasn't the question at all, but that's super helpful.
Wow, I really love that last comment he made. That really wasn't the question at all, but it's super helpful. That's what he said. And so here, what's going on is he knows that that's the linchpin of the rest of this problem. As soon as you know that, you're off and running because you can say, oh, well, wait a minute. The 2 kilogram box must be accelerating that way, and they stay connected. The 5 kilogram box must be having that acceleration. That's the key, right? And so he knows that this is the most important step of the problem, and yet what he just said was, oh, it doesn't seem useful. So I think it's really interesting to get students to realize that times you have to go over here before you can come back to what you were originally asked. And when you go over here, I don't know which way I did it. When you go over there, you're usually going to a comfort zone, like, oh, I know how to do this. Let's just sum the forces, see if it's useful at all. Now, sometimes you sum all the forces and it ends up being 0, and you're like, oh, that was a waste of time. But in this case, it was the linchpin. It's absolutely the most important part of this problem, at least so far. So I think that it's really interesting the way he couched that. Awesome.
Because now I can start figuring out these contact forces, just like I could figure out the tensions in one of the problems with strings.
I love that connection.
Now I pick a block, and
Change your color.
I could pick either block. I could pick the green one or the blue one. I'm going to do the green one. So I do the same thing I just did, except now I'm going to use the values just for this system. So net force for the 2 kilogram system is mass times acceleration. So 2 kilograms times everything accelerates at negative 3.
Hey, I fixed it.
So that's negative 6 newtons. So that's the net force. And the other way to get the net force is to add up all the forces that are acting on that block. So I've got the contact force, I've got the weight, I've got the normal force, and then I've got this push here. I'll just call that F. So that's the push. And the things that don't cancel, the weight and the normal force cancel. The 21 Newton push and this contact force, those don't cancel. So I'm going to add those up. Think about which one's positive. I'll write that one first. That would be the contact force because it's pushing to the right.
So the answer is going to be 15, it looks like, right? And so it's amazing that the 21 is almost entirely, I mean, that's a healthy fraction, right? Almost entirely being rejected by the 5 kilogram box. And so it's really being a bully here. The 5 kilogram box is saying, oh, man, don't push me, I'm going to push you right back. And it's so interesting to realize that these contact forces, oh, they just cancel, students maybe don't care about them. It's actually huge and a super important part of the problem.
And I'm going to subtract from that the main force, which I could have just written as 21. So let me write that again a different way. I'll say the contact force minus 21 newtons. So this is the net force based on F equals ma.
So I see a potential sign problem that he's got. So he's got this negative sign here, and really his force, because it's to the left, should have a negative sign, which he did here. So I'm really curious to see whether he just says this is 15, or if he says it's negative 15, or if he says it's negative 27, right? So I'm really curious to see how he fixes this. And we all have this, right? We introduce a sign convention that means one thing, and all of a sudden, oh, hang on a second, that's not what I meant. Sometimes what I'll do is I'll say, come on, we know what's happening. It's pushing against. It's got to be less than 21, right? And in absolute value, and we'll figure out the direction later. So I think that it's fascinating to think about how to deal with a convention that you have started to use that then you don't use appropriately. Are the students going to say something? How is he going to fix this? And I think this is an important moment, because come on, we can't be perfect, and we need to be able to gracefully handle these situations. So let's see how he does it.
This is the net force based on adding up all the individual forces. So I have contact force minus 21 equals negative 6. So I know somebody can do the math in your head. What's the contact force?
So really the issue is this negative sign. So so he said that F was 21, and then he said, but we should subtract it. So that's fast. And actually, I think I just missed it when he wrote that. So that's actually really, really an interesting way to do it. Because when he said it out loud, he said, well, we know that contact force minus 21 equals negative 6. We're like, okay, so then the contact force has to be positive 15. And so that's because he put this negative sign here. But look at this, just look at this here. This is a really interesting statement. It's a summation, and yet there's a minus sign. So this idea that he said, well, F is 21, but I'm going to have it be subtracted, that's actually where he fixed it. And interestingly, I missed it. I was probably talking, right? But it's kind of interesting to think about how students might look at this after the fact and say, huh, what? And so I think that he's going to do a great job of explaining, oh, yep, 15 is, there's somebody pushing back. So just watch out. I think that when you make a sign convention, and he's actually stuck with that. I was in the wrong here because he did this absolutely correctly based on what he said F was. There's actually nothing wrong here. But it's interesting to think about, what would students think? And so right now he's calling out, does any students get it? Let's see what they say.
I feel like we've missed the window. 15. So if you set this equal to that, you just add 21 to both sides. So contact force is 15. So there. So I can write equals 15 newtons. And that means this contact force is also 15 newtons. It's gotten a little bit messy there.
So I'm going to stop there. We're pretty long here, but I think that there's some really, really fascinating things that he's doing. First of all, really sticking with the fact that the contact force is the same, equal and opposite. I think that problems like this, he's doing such a great job of talking about, wow, we just have to use our tools. These are the tools we know. Let's see what we can do. And we're finding fascinating things, right? So pushing with 21 newtons, but something else is pushing back. I just think these problems are so cool. And I thought that the way he set it up and the way he's dealing with it was really, really interesting. So thanks, everybody. Have a great day. And remember, physics teachers are awesome.